Swayam Prabha. Digital India. Educated India.
Welcome to this session. Earlier we have learned about the phase error analog and digital phase error detectors. So far in analog we have seen mixer and sample and hold. Okay. In case of digital, we have seen exclusive XOR, exclusive OR gate. We have seen here SR flip flop based. Okay. Phase error detector, and we found the linear range and other things. Now, if you look at it, that the range in both these cases, whether you are looking at the analog or digital, let us say digital only, in both these cases, what you see here is that the range is actually limited. So, given the R and V input signals, what you see here is that the linear range is either 0 to pi by 2 or 0 to pi at maximum in case of digital. So, what can we do if we would like to extend the range of the phase error detector? Okay. So, one thing is, the question which you need to ask is how to extend the range of phase error detector, range of PDs, I can just write it directly. Okay. So, for example, you have your PD, I will just draw it as a block, it can be your XOR gate, it can be your SR flip flop here. We are just right now looking at square waves. So, I will limit myself to digital. This is R and V, and we are talking about the clocks which are having the same frequencies for now. Okay. So, it gives you VPD output. So, here just to recall, what you have seen earlier is that with respect to the phase error between the R and V signal, your VPD average was either like this, okay, that was your XOR case, or it was like this. Okay, on the positive side. On the negative side, you will follow the similar characteristics. So, this linear range is, this is pi, and by the way this is 2 pi, it does not extend more than that, right. So, what I want to do is, actually I want to extend the range of the phase error between R and V signals. So, the PD which we are having, that operates on these two. If you reduce the range, if you reduce the frequency here for R and V, then your range will actually get extended. So, what it means, let us see. So, let us say I have my actual R and V signals like this. Okay. And the V signal has, it has the phase error, that is fine. The frequency I am keeping the same. If I divide these frequencies and get outputs R dash and V dash, so if I do that, what will happen here is, this is our R dash, this is like dividing the frequency by dividing f by 2. Similarly, your V dash is going to look like this. This is dividing the clock by 2. In digital case, you might have seen this operation quite often. This is V dash. Okay. So, the phase error which you have between R and V, that phase error remains here. The only thing is it is measured now at half the rate. Now, if I give these R and V signals, if I give R dash and V dash signals to the bang bang PD, what I will get, I will measure the phase error between R dash and V dash signals, and this phase error between R dash and V dash signals, looking at the plot here, 2 pi phase error for R dash and V dash signals is same as 4 pi phase error for R and V signals, isn't it? So, because this 2 pi phase error for R and V signals is actually time period 2t, right. Here this 4 pi is measured with respect to t, here this 2 pi is measured with respect to 2 times t. So, that is the way you can do it. So, what can be done? So, if I get my R signal here, I put a frequency divided by 2, okay, and here I put also the frequency divided by 2, and I can. So, this can be our new phase error detector with extended range. Okay. So, let me just redraw this. So, what we have with the divided, so I am going to measure with respect to R and V my phase error, okay, VPD average. So, for XOR gate, VPD average, now this is going to be 2 pi and pi. Okay. VPD is the phase error is measured between R and V signals, keep that in mind. And for our SR based stuff, that is going to be 4 pi. Okay. This should not come like this, go like this, and the red one is here, right. Whereas, if you think about with respect to R dash and V dash, so phi R dash for R dash and V dash signals, this pi is nothing but pi by 2, this is pi and this is 2 pi. Okay. Because we are referring with respect to the original signals, that is why what you see here is that the range gets extended. So, if you want to extend the linear range of the phase error detector in case of these two digital phase error detectors, you can do it by having divide ratio. Well, if it sounds good, there is a drawback of it, and the drawback is now you are measuring the phase error at half the frequency. Okay. So, if there is any phase error here in this particular case, well, that phase error will not be entertained in case of your SR based PD. Okay. In case of your XOR based PD, what will happen is that is going to change the duty cycle, and the duty cycle they will then affect the phase error. But your rate of measurement of the phase error reduces as you try to extend the range of the phase error detector in this case. Okay. Thank you.